Okay, so let's just give you a some background of why we are covering this. Um, so if you check your Canvas site, I posted an assignment related to the project today. I gave you some extra time because I think March 31st is just too close for you to be able to gather the data that you need for the project. So I extended it to April 4th, I think, which is April 2nd, which is Wednesday, right? So you have a little bit more than 2 weeks to gather the data. So please, that's not the due date. This is the file that I posted at the beginning of the semester. The due date for phase two is April 2nd. So you have some extra days to complete the report. Okay, so what you're going to be doing for phase two is to collect data from the system that you are going to be studying for your project. What type of data? That's what we're going to talk today. Okay, so this is in order for you to be able to input the probability models that you need for your model, you need to gather that data from the actual system. So you're gonna collect plenty of data so you can so that your estimates are statistically reliable. When I say enough data or plenty of data, that should be at least between 125 observations per area. Like for example, if you're looking at the arrival process, collect about 125 observations of arrivals. Also, if you're looking at the processing times, you have to gather at least 125. Those, they don't need to happen on the same day as long as you are observing the same time period, right? You can go, if you're looking at a restaurant here at the university, demand is almost the same from Monday to Thursday. So if you go, let's say between 12 and 1, any day from Monday to Thursday, you should see the same amount of people showing up. Fridays are slow because we don't have a lot of courses on Friday. So I would not, like, if you go on a Friday, unless you're observing only Fridays, your observations are going to be different. The data is going to be somehow biased because you don't have the same type of demand happening on Fridays. So my recommendation is to, if you're looking at the restaurant here at the university, to schedule your observations between Monday and Thursday, and then to set up the timeline to be the same. So you are gathering data. Let's say if it's lunchtime, it's lunchtime. If it is dinner time, so dinner time. So everything is consistent. So if you say 150 and you want to go for 3 days, then I will do 50, 50, and 50. I'm done for that process. And then go the next week, do 50, 50, and 50, and done. I think you should be able, if the restaurant is busy, you should be able to get that in less than an hour. So you will not be able to collect more information later, right? So you make sure that you gather as much information as you need. For best results, be sure the system empties out at least 3 times during the data collection. So that will be kind of difficult. If you can see that, I will say in the afternoons, that might be the best time to see the system empties out. If not, you're going to be there for a long time. So if that's possible, you can try to stay until that happens. But if not, I'm not forcing you to do that. Since your objective will be to propose these design changes that will result in reducing the average time spent on the system, it is crucial to collect data to estimate the time spent in the system. Although this is not an input of the simulation, the reason we need to collect this type of, we are gathering information to build the input models for our system. but at the same time, we're gathering data to validate our simulation, right? So, for instance, when you're observing the arrival process, you're looking at, okay, this person arrived at 10 or 11:01. This other person arrived 11:03. This person arrived 11:05. So you're keeping track of the arrival. We're going to use that times to compute their inter-arrival times. In some cases, you will have people arriving in groups. So if that's the case, I will try to keep also a tally of how many people are arriving. So if they're by themselves, okay, that's fine. But if three of them, let's say three friends shows up to the restaurant at the same time, you can put the time they arrive, and then next to it, you can say 3 or 2. So you keep track of the number of people that are showing up. Then after you get the observations from the arrival process, you can transition to observing, let's say, the time it takes for a cashier to serve the customer. And you can, those are a little bit more, I'll say, difficult, because if you have more than 2 cashiers, then you might not be able to observe both of them at the same time. So if you only have one, then it'll be easier. So you focus on how long, so you need to have some type of watch or your phone with you, and looking at how long it takes for them to take the order. And if the same person is in charge of setting up the order, then that's another processing time that you need to observe. So this instructions that I'm providing, they're going to be different for each one of you. The important thing is that you know the difference between the arrivals and the process. Like if you only have one process, then you only observe that process and you take time for that processing time. But if you have a cashier and a person setting up the orders, then you have to take processing times for the cashier and also service times for the person that is setting up the meals. So most of the time you will have those 3 areas that you have to gather data: arrival, process 1, and process 2. The last part will be if you are able to track one customer from beginning to end, right? It's like this person arrived at this point, and that same person left the system at this time. That is the total time in system. And that's the time that we will need to validate our simulation. That makes sense? Like, I need to know how long these customers are staying between arrival and departure. Because when I run my model, I want to check if my model is also showing that same time or close to that time in system for the entities that I'm representing in my model. And if that's the case, then I can have we will use the time in system, and we also gonna use the number of customers served during a specific time period, right? So we need to have those 2 metrics or some information about those metrics from your system. So by the time we run our model, we can compare those metrics with the simulation results. And if we have a simulation that is representing the same metrics, then we can validate our simulation and then move to the final part of the project, which will be to use the model to make some interventions and see if we can improve. Let's say adding another cashier, adding another cook, or any other type of suggestions that you have for the system. We can test it now that the model is validated. So on the next page here, you'll see that I have an example of how that process will look like in terms of collecting the data. Right, so for example, consider a small fast food establishment where there was just one person who took the order, fixed the meal, and took care of the payments. Some customers arrived individually and some in groups, waited in line, and were served one by one. So in this data collection sheet, we have 5 columns. We have the customer number, the number of people that arrived together, the time of arrival, the time the service starts, and the time the service finished. So for example, in this first person, we have a little wait, actually. They arrive at 13:10 and they leave in less than a second, right? So that's kind of interesting unless they have the food ready, unless that's a typo, I apologize. But the second one makes more sense. So there's no queue, they get served, and then they wait about 12 seconds to get the service completed. And then you move forward until you get to that 150 observations. What are we going to do with this data? Okay, once we get this information, there are multiple things that we can gather from here. First, the interruptible times. Let's see. See, I can look at these two numbers. Right? If I look at the difference between arrival 1 and arrival 2, you see there's 46 seconds, right? So that's the interarrival time. And I'm going to be doing that for each of one individually. Yes, sir.
So we are tracking each customer.
Mm-hmm.
So we're tracking 150 customers when they arrive, how much time they take for that.
Yes. So that's what I was. You're only one person, and it will be very hard for you to track every single person, right? So getting something like this will be very difficult. However, you can, as I said at the beginning, you can focus on this first part, right? One day or for the first part of your observation period, and then move to the second portion. We know there's going to be different customers. That's okay. As long as you are observing during the same time period, you should be, the data should be consistent, right? And most of the restaurants that you are observing are serving food that are very similar, right? That's burgers, tacos, or I don't know. So it will not be orders that differ a lot in terms of the preparation time. Yes, sir. Yeah.
So I'm assuming that we're gonna have to fit a distribution to describe the interrupt
Yes.
time at some point. Are there gonna be clear guidelines on how we're supposed to do the fitting of the
Yes.
because that probably is
Yes.
one of the biggest.
So that's the second part of today's lecture. Yes. So I'm starting with why are we doing what we're gonna be doing? So that's a good question. So yes, after you collect all this information, then we are going to input the data, the resulting data, into the input analyzer, which is the second part of today's lecture. So for the interarrival times, I just want to make sure that you understand what we're going to do. For the interarrival times, we're going to be subtracting observation 1 from, or observation 2 from 1, and then 3 from 2. And you're going to create a new column with that information. Those are going to be your interarrival times. When we get to the service, it's not row difference, is columns differences. So now we're going to look at the processing times. So for that, we are looking at the difference between these two, right? So first processing time is 1 second. Second processing time is 12 seconds, and so on. Yes, sir.
Sorry. In between the time of arrival and time to start service, that's gonna be, I'm assuming, the setup time.
Oh, yes. So between time of arrival and those times should be the same,
Okay,
right? Because you
show up and you start to get.
yes, once you are, well, if there's no queue, you'll go right away.
Right.
That's good observation, but I'm not interested about that time.
Okay.
Because that is the time that is resulted from the process, right? So it depends on how many people you have in queue. At the end, it should match, okay. Right? So this processing time And the arrival process is basically what's going to determine the queue of your system, right? If you have a processing time that is very fast, it's faster than your arrival process, you know that no queue will be formed. But if it's the opposite, you know that queue is going to be formed. Yes.
So if we're taking data in 2 different days, first of we are collecting time of arrival and later day we time of finish the service. Then we are assuming that the time is fixed. Like when they arrive, they are start taking the service. There is no queue.
Yes, when you're doing this part, this processing time,
Arrival
you're
time
just
equal
looking at the processing.
Yeah.
Forget about the queuing.
Yeah.
Okay, just I mean, this person is they're taking the order starting right now, and they're done after 10 seconds. Because at the end, that timing queue will be determined again by the processing times and the arrival patterns. Okay, the queue size also is going to depend on those. So as long as we have those distributions collected or the times collected, we're going to gather data, and we're going to input that and get the corresponding probability distribution for both. Yes.
For most of the restaurants, there will be no setup. But for other processes that do have setup, do you expect us to model also the variability in the setup? Because setup time, in my case for 3D printing, it will be taken into account whenever they're initializing the printers. And that could vary very greatly between the technicians and the type of work that you're trying to do.
Yeah, so I will try to be as consistent as possible, meaning that if you're gonna be observing a process that have multiple technicians, that you make sure that you observe one technician, not multiple technicians, because that will add more variability, and you will need to gather more data in order to get the right values. Yes.
So for it as consistent as possible.
As consistent as possible, meaning that you are observing same time period, same day, if possible. I'm talking about your case specifically.
Yeah.
Again, for restaurants, I'm pretty sure that Monday to Thursdays are very similar. In your case, maybe there are differences between Mondays, Tuesdays, Wednesdays. So I'll try to be as consistent as possible when you're gathering that information. Okay, so at the end, we will have data in terms of arrivals and processing times. From here, you can gather things like how many people were served or expected to be served on, let's say you're observing for half an hour or 1 hour. Try to collect data for the same amount of time. So if you're going to be observing for 1 hour, try to stay for 1 hour for the days that you're observing, right? The time period that you're observing is important because you're going to be running your simulation for that same time period. So one hour, stay for 1 hour the next day, so we can use the same replication length for your simulation. Okay. What else? Okay. Nobody has asked about numbering group, but let's say in your case, you end up having a lot of variability in terms of the size of the group. We can also fit a distribution to the size of the groups, and we can put that in the create block. There's a space that says number of entities created. We can also put a distribution there if there's a lot of variability, and that distribution could be based on that information. So we can also fit a distribution to that. What else? Yeah, so that's in terms of the data collection. Again, I'm gonna be available to answer questions. So if you start setting up everything and you have questions, send me an email, and I will gladly answer those questions. Please try to use this week, next week to collect the data, so you are not running out of time towards the end, because my experience tells me that if you leave till the end, you're gonna start next week. By Friday, you're gonna start trying to fit a distribution, and you might not get a good fit. Then on Monday, you're gonna be stressed out. Hey, what do I do? I don't want that to happen. So if you can gather lots of information this week, then next week we have time to check where you are at in terms of fitting, not fitting, and so on.
What if we have any customers leave during the time of arrival and then they just decide to leave?
Yes, so those customers, we can keep track of those. That's a good point. Like, let's say you have a queue that is very long. Someone shows up and they decide not to stay, they leave. We should keep track of that. So if you see that happening during your process, you can also make a note. There was customer leaving at this time. So we can also put that in our simulation. We can say, for example, they arrive and there's a 0.01% chance that they might not continue. So we can branch them and discard them and count them as part of the simulation. Yes, very good point. Yeah, so that can happen as well. Any other question?
Do you have any principal objection to us using data that we didn't collect but does describe the system?
Yeah, so my concern is I want you to be able to experience the data collection process, right? So I want you to go through the experience of looking at the system, use the clock, put the observations. So if you have a way to automatize that, somehow make it automatic, I still want you to be there to make those observations. Yeah. I have students that have recorded. I mean, it depends. Like if you are recording from a distance, the process, and then just watch the video, I think that can also work. That helps you be more specific in terms of just don't do it so obvious, like people will get scared, you know? If you're using your phone, you can set up the phone in a way that you can record the process and then use that video to gather the information. I'm not opposed to do that. So again, those are techniques that are also used in industry, that you will have cameras observing the process, and then now with artificial intelligence, I think will be even easier to get the information that you need. So yeah. Any other questions? Good. So let's talk about the input analyzer now. So again, these slides are posted on the module for today. And it's actually a tool that is very simple to use. Is part of the Arena software. When you go to the Arena software folder and you open that folder, you'll see there's the simulation software, but there's other software packages as part of the folder. One of them is the input analyzer. But before we get into using the actual software, I want you to have some background in terms of the numbers that are going to be showing up in your analysis. So these are three things that are important that I know that you have seen before as part of your statistics and probability classes. Hypothesis testing, p-value, and the square error. So what is hypothesis testing? Again, as a review, is a statistical decision-making tool in which you have two complementary hypotheses that are formulated. You have the null hypothesis and the alternative hypothesis. And a decision is applied to the null hypothesis, which is either accepted or rejected. I have professors that they never use accepted. They say do not reject or reject. right? Because you're never 100% sure if you should accept the hypothesis or not. So you might see textbooks using accepted, some textbooks not using accepted. Consequently, based on that, there's two types of errors that are possible. Type 1 error, which is rejecting that null hypothesis erroneously. And type 2 error, which is accepting or not rejecting the null hypothesis erroneously. Okay, so type 1 and type 2. The goal of the hypothesis testing is to reject the null hypothesis such that if the null hypothesis is in fact true, then the probability of erroneously rejecting the null hypothesis do not exceed some prescribed probability that we typically call alpha. This is called the confidence level or the significance level. Okay, so we want to make sure that if we are not rejecting that probability of us being wrong is very small, right? And that's what we call the confidence level. The smaller is this alpha is, the higher is the confidence in a corresponding rejection decision. So here's an example. Suppose that we wish to compare the failure rates, delta 1 and delta 2 of machines 1 and 2, respectively, at a significance level of 0.05. And we had two hypotheses. The null hypothesis is saying that delta 1 is less than or equal to delta 2. And the null hypothesis is saying that delta 1 is greater than delta 2. The modeler forms a test statistic T from some observed data with a known distribution under the null hypothesis. The state space S of T is then partitioned into two disjoint regions, right? So we typically have a curve. We're going to mark that area in which we have a rejection region. And that state space is basically the union of the acceptance or do not reject region and the R1, which is the rejection region, such that the probability of type 1 error does not exceed this significance level. In practice, the analyst computes a realization of T and decides to accept or reject the null hypothesis according as T fell in both of the in one of these two regions, R0 or R1. So you should remember you setting up the curve for the T statistic, finding out that T value and marking the acceptance and rejection region, and then computing that statistic for your data. Yes.
So we are comparing delta 1 and delta 2, whether there is a difference or not. So why are we not taking now this as there is a difference, like delta 1 greater than delta 2? Why we're taking delta 1 smaller than it was delta 2?
So you're asking about the direction of the signs? Yes. So compare the failure rates between delta 1 and delta 2. And yes, the hypothesis. Yeah, so it can go either way, right? So suppose we should compare the failure rates of machine. The hypothesis. So basically the hypothesis that we want to test is that the failure rate for 1 is less than or equal to 2. And that's based on the modeler's decision. I don't have the whole background about the example, but yeah, that's something as a decision maker or modeler that you're basically setting up your experiment that way. Yes, sir.
Just to verify, are
Mhm.
we gonna have to identify R1 and R0?
No,
Okay. 'Cause-
this is just background for you to understand why the software is giving you that number and why are you making a decision based on that number. Okay.
And whenever we're posing a hypothesis test, are we always gonna have to set it up as a one-tailed test?
No,
Okay.
that's going to be based on the experiment that you're setting up as a modeler. Yes. Okay, so we know now, we review what the hypothesis test is, right? And then what error 1, error type 2 is. Now let's talk about the p-value, which is an alternative approach to a hypothesis testing. This computes the probability value or p-value of the realization of the test statistic t, where p is the smallest significance level for which the computed test statistic t can be rejected. Okay, so it's a lot of words there, but basically what we are trying to find out is that probability that is gonna make sure that we are making the right decision. We want that to be the smallest one. So in hypothesis testing, we fix alpha and then decide whether to accept or reject, depending on the region in which the test statistics fell, or t fell. Conversely, suppose that we do not fix alpha before computing the test statistic t, but allow it to float. We would like to know how small can alpha be made and still permit the null hypothesis to be rejected. This means that we seek the smallest alpha that rejects the null hypothesis. The p-value contains a considerable amount of information on the quality of our test decision. It decides whether to reject the null hypothesis or accept it, but we can also obtain an idea how strongly we reject or accept the hypothesis. The smaller p is compared to alpha, the stronger it is with rejection. Conversely, the larger p is relative to alpha, the stronger it is the acceptance or the not rejection. So p-value for the test statistics and best fits, measure of fit, the larger, the better. The larger p-value means that we have good fit. Small p-value means that we have a poor fit. Many software p-values are as the ranking measure to automatically determine the best fit, but we need to be cautious about close conformance to the data does not always lead to the most appropriate input model. And two, p-value does not say much about the lack of fit when it occurs. So our recommendations is always to inspect the automatic selection using graphical methods. So typically what you're gonna see is you're gonna be generating a histogram, and what you're trying to do is based on the PDF or density functions of different probability models, you're gonna try to fix that curve to your histogram. And the density function that has the closest fit in terms of meeting the changes in your histogram typically is the curve or the probability distribution that will give you the best fit. So that's why it's recommended for us to make sure that we're looking at the curve and how it fits to the histograms. So that's something that the input analyzer will generate for you. It will show you the histograms and also how close the PDF is based on the best fit. Finally, we need to talk about the square error. This is some of the square discrepancies between histogram frequencies and the fit distribution frequencies. So again, what we have, as I was saying, you typically will have a histogram with your frequencies for the data that you observe. And then what the software is going to try to do is to fit a PDF based on the shape of those probability distributions. So what the square error is looking at is how different in terms of distances are those fits. So it's going to look at the distances between those histogram bars and the curve. And it's going to make an estimation in terms of the measure of the goodness of fit of a distribution to an empirical data set. Okay, so that's what we have here with that E square value. J is the number of cells in the histogram. P hat J is the relative frequency of the J cell in the histogram. And PJ is the theoretical frequency. So we can compute that and get the estimate in terms of the squared differences between those values. And that's the square error. Okay, so that being said, we can now look into what the input analyzer is providing us. So this is a separate application, also via the tools menu in Arena. And will allow us to fit these different distributions. I mean, I think it has about 12 different distributions. The user has two options: specify a particular distribution and request the associated parameters to that distribution, or request both the class of distributions as well as the associated provided and find the best fit. So if you want to test one distribution at a time, you can do that. If you want to test them all together and ask the software, tell me which one is the best, you can also do that. Here's the list of Arena's reported distributions for the input analyzer. Yes.
Are we expecting a better solution for the estimation of parameters if we already tell it what the?
No.
Okay, so it's
No.
gonna be exactly.
Yeah, it gives you both options in case you wanna, okay, I wanna make sure, or I want to see if I can use the normal, for example. And then you go straight to the normal and see how good of it fit it is. But the answer is we typically go for the best fit, right? And it's gonna be based on a ranking, and it's gonna be based on some of the metrics that we just discussed. So the exponential, normal, triangular, uniform, Ekland, beta, gamma, Johnson, log normal, Poisson, Weibull, continuous and discrete distributions are available. We also have an empirical distribution that is not obviously listed here in this list, which I will talk a little bit more maybe next week. For those of you that are not able to find a good fit, that will be like our last resort. Like we're gonna fit this empirical because we have no other option, but we would like to get a good fit. We try to shoot for that good fit first. So fitting the distribution to the data with the Arena input analyzer, we're gonna have sample data that is gonna be independent and identically distributed. That's our assumption. Typically, it is a good assumption based on the systems that you're gonna be observing. We want to select or fit a probability distribution for use in generating the inputs for the simulation model. So if you go to Canvas, you'll see that there's two files. One of them, for today's lecture, one of them is an Excel file. If you can download that file will have this data. Okay, so we're gonna use the input analyzer, and the data that we're gonna use is the data that is there. So if you open that file, these are the observations that you are going to see. And let's say we want to fit the uniform distribution to this data. The type of report that you're gonna see is here. Okay, and we're gonna do that in a minute. I just want to give you an idea of what you're gonna observe. So you're gonna get the histogram. That blue line that is cutting the histogram is the fit. So since we are trying to fit the uniform, that's the shape of the uniform, is that horizontal line. And then based on that distribution, we get certain statistics. So using the fit menu and upon selection of a particular distribution, it provides the graph, the parameters of the fit distribution. So these are the parameters that we got for that distribution. And the statistical outcomes of the goodness of fit tests employed. So for example, here, we perform two tests. We get the chi-square and the KS test. And you see the p-values here are above 0.05, which is typically what we are shooting for. So they're saying that this is a good fit for this histogram or this data. And also provides you with some additional information in terms of the data points, the minimum, the maximum, the mean, and the standard deviation. What I want from you in the report is for you to provide me with your data. And I think I posted in the assignment, there's an example of a report there. You can refer to that example. But I want to be able to observe your plot and also this information as given by the software. So if you can do a print screen and put it in the report, that would be great. Chi-square, do you remember when to use one or the other? There's a difference. I mean, both of them are used for the same purpose. Arena Input Analyzer give you both. But there's at least when I say it again. But it's more in terms of the number of observations. Like one is more reliable for smaller sample sizes. The other one is more reliable for larger sample sizes. So KS typically is good for larger sample sizes. And chi-square for smaller. At least that's what I'm recalling from my courses. So yeah, but in here is both of them are provided and both of them are telling you got a good fit. P-values are good over the 0.05 rule or yeah. So let's see, we'll now open the input analyzer. We'll go through this process. So again, I just wanted to, in case you forget, as a rule of thumb, if this p-value is less than 0.05, that means that's a poor fit. Okay. So you want to get at least 0.05 or greater in our fit to say that this is a good fit for our data. And then once that is observed, then we will get this. Like if you get a good fit, this is the distribution that the software is giving you. So that's what you're gonna copy and put into your system or in your model. Like in this case, it's uniform 10 to 30. So that's the distribution that you would use for the process that you're observing in your system. Okay, so okay. I think we can go to the input analyzer. So you can search for it, input analyzer, and then open the software. And again, I'm recording this. If you have questions, I'll make the video available for you to review. I think there's more videos available on YouTube about this same topic. So if you don't see my video, you can find them also. So the first thing we're gonna do is to create a new project, right? So you can do that two ways. You can go here, file, new, or you can just click this new button here, and that will give you this. Now, before we get to work with the input analyzer, we need to make sure that we set up our data in the right format. So the input analyzer will use data in .txt or text file. As long as we save it in the right way, so it could be tab delimited.txt. As long as you have a way to separate the data. So how do you save the model or data in that way? We can save a copy, go here, find your location, right? So let me find the desktop in my case. And then you have a lot of options here. I will use the text tab delimited. As long as it is .txt, should be okay. So I'll save it as text. And then I'll put a 3 here and save it. You'll get this message basically saying, I have multiple sheets. I'm only saving one sheet. That's okay. I don't need the other 2 sheets. So, and then I can minimize this, go back to the input analyzer. This is the step that I think most of you will forget, or at least based on my experience. Every time that I use to use the software, I need to review this part. How do you bring the data into the input analyzer? You go to File, go to Data File, and then click Use Existing. And then you'll go find that file that you just created and click Open. Okay, so you'll see that once you open that file, you get the histogram and you get the data summary, how many observations, the minimum, the maximum, the sample mean, standard deviation. And this automatically use a 10 as the number of intervals. That is something that we can also change. That's something that I advise the students to do. If you're not getting a good fit, you can change the number of interval and see if you can get a better distribution of the data. How do you do that? You can go to options, parameters for the histogram. And instead of 10, I can say I want 15. You see now I have a different shape for my histogram. The default will be okay. But if you experience problems, playing with the number of intervals can also help and see if you can get a better fit. So yes, sir.
Once I find the optimal distribution, would changing with the amount of intervals impact the parameters of the distribution?
So at the end, what we want is to get a good fit for our data, right?
Okay.
So if you can get that good fit from the beginning, you don't have to change the number of intervals. You use the default value, right?
Right.
Because the distribution is going to be based, the distribution will give you parameters that are going to be a good fit for your data, right?
Okay.
If you cannot get that with the default, then you can try to change the number of intervals and see if by adjusting the number of intervals, you can find a distribution that fits the data. Yes.
It's simply a histogram. We can create a histogram using Excel. So why use it?
You can use,
You can create a histogram using the data in Excel.
yes.
We are testing there.
So how do you test for the distribution? Yes. So up to this point, yes, you can create histograms, but now we are moving to the purpose of the lecture, right? Which is to fit a distribution. So to do that, we have multiple options here. Like fit all, you can go there, right? So let's do that. So when you do the fit all, it will show you the fit of the best distribution. In this case, p-values are about 0.05 for both the ks and the chi-square. One of them is 0.41, the other one is point or greater than 0.15. So this is telling me that this expression that has a beta distribution is the best fit for my my distribution. However, I can look at this fit all summary and see which one is out of the list that is provided by Arena, which ones are giving me good performance. And this is a ranking based on the square error. So you see the beta is first. We can also try to fit the normal, I'm sorry, the uniform and the normal and see if those two distributions can give us a p-value above 0.05. So let's look into that. Cancel. Thank you. Yeah. So now I can go to fit the uniform. Right, so the uniform is also good as we saw in the slides, right? It's not better than the beta, but it's still good. P-values are about 0.05, and we get the uniform 10 to 30. It's a good fit. What was the other one? That was a normal, I think. So normal, you see, when you look at that plot, is not very good fit, right? Because you get the sides are too low and the middle part is above those bars. So when we look into the p-value here for the chi-square, it's telling you that it's not a very good fit. Okay, so for this data, we have two options. We have the beta and we have the uniform. If you decide to go for the beta, then the expression that you have to use includes that 10 plus 20 times beta, right? So you're gonna have to copy the whole thing and put that into your model. So it goes from the 10 plus 20 times beta. So the whole thing is part of the expression. What else? Yeah. Questions? So that's essentially what we are trying to do. We are collecting data. We are cleaning up, organizing the data. Once we have that, we can set up the data file into a text file, feed that text file to the input analyzer, and then use the input analyzer to check if we can get a good fit for the distributions that we have available. And if that's the case, then you're done with that data set, and then you move to the next one. Yes, sir.
So the original data file is 5 columns. Each one of them has, it seems like 20 members.
Mhm.
They're not, there's no naming, there's no,
Mhm.
any of that. So first of all, do we need to make sure that there's no column names whenever we're?
Yeah, it's just data.
Okay.
Yeah, that's a good question. Yes.
Second thing is, are all of these columns representing the same data?
So when you build this histograms, basically you're creating bins of values, right?
Right.
So I don't know what will be the minimum here, 10, and then the maximum is 30. So you take from 10 to 30 and you create bins between 10 and 30. So in this case, you divide 10, 20 divided by 10, you have bins of 2, right?
Okay.
And then you're counting how many observations are in the first bin, second bin, third bin, fourth bin, up to the 10 bin.
Okay,
And that's how these columns are formed.
right. I'm asking about to clarify what I was asking,
Mhm.
is the Excel file like just processing time for a specific process and it's?
Oh, so you're talking about the actual meaning of the
Yes.
data?
Yes, sir.
That data is just randomly generated. It's not representing anything
Okay,
right now. right? But it could be easily processing times.
Okay,
Yeah,
and it all would be the same processing time. 'cause
all
you're
processing
describing
times,
the same
yes,
process.
just for that processing time. So if you have two process and one arrival process, you'll do this for the arrival process, you'll do this for the first processing, and then you will do this for the second process.
And the last question
Yes.
is, if all of this information refers to the same process, does it have to be in a specific structure? Or can it just all be in like one long column?
It doesn't matter, because once you put it in the text file, as long as there are
The numbers in
somehow
there?
set up in a way that you can read them, yeah, it should be fine. It will tell you, like, if you want to make sure that your format is consistent, it will tell you the number of observations that you have. If you notice that you're missing some values, then you might need to check your format.
I see that. Okay.
Yes, yes.
Thank you.
Any other question? No more questions. Good. So again, that's all for today. I want you guys to make sure that you get into the data collection for the project, and that you ask me questions as soon as you start getting into problems with your fitting or with the software. Make sure that you reach out so I can clarify. Most of the time, if you cannot get a good fit right away, like I will go, if I were you, I'll go 50, 75 observations and I will try to fit. If you can get a good fit right away, email me at the Perez. I did 75. I got a good fit already. That's good. Then you can move to the next process. Yes.
If I collect like 100 data,
Mhm.
100 arrival data, then potentially I will have like 50 inter-arrival time, right?
No. It's 99.
I just, oh yeah.
Yes, 99. So it's 1 minus
Yeah,
the
yeah,
total. Yes. Yes.
And I put that data into this analyzer, right?
Yes. So anything, make sure that if you have an arrival, that you get a sheet of data for that. For the processing, a separate data sheet, and for process two, a separate data sheet. Right? And you get a separate number of observations for each one.
First at the beginning, we have 0 in the time.
At the beginning, once you start observing, that first observation might not, it will only help you for the second. If you're looking at the inter-arrival time, right?
The data like input data
Mhm.
to the input analyzer, then there will be 100 column.
Okay, so remember that for all of them actually, but for the inter-arrival process, that data that you're collecting is not the one that you're gonna enter. What you're gonna enter is the differences, right? Right. So that's the data you're gonna input. Another thing that I forgot to mention is if you collect times, like hour, time, minutes, and seconds, and that's the information that you're putting into Excel, make sure that you know how to get the difference between times, because it's not as simple. Okay. So I mean, I don't remember exactly how to do it. I know there's a way to do it. Yes, but make sure that you know, because if not, you might get into problems when you're trying to look at the differences in time. Or if any of you know, that just talk to one of your classmates. But yeah, that's another thing. It will take time to figure out. So if anybody of you knows and you can share that expertise with your classmates, that will be great. Also, and the final thing, this right here, if at some point you need to generate data, which I don't know how useful that could be, unless you're doing an exam and you want to test, you can generate data following a distribution. You can tell the software which distribution you want to use and the number of data points, and it will create that data file with following that same distribution. So that's another thing that is there. Yeah. Good. Okay, so I'm stopping now.